Hi, welcome to the sharing session of CoSpace Rescue Vision Simulator. My name is Paul. The content of this session can be divided into 4 parts. First, I will introduce CoSpace Rescue Vision Simulator to you. Second, I will explain the features newly added to the Vision Simulator. In third part, there will be a discussion on a basic navigation program, which will be accompanied by the Vision Simulator itself. You can get access to this program when you install the platform on your device. And in the last part, I will try to summarize and conclude the session. Let's move to the first part. In the current world, you can see applications of vision in many places. It can be used in machine vision and for facial recognition, or even to detect whether a person is wearing a mask or not in this COVID time. Other areas of use includes self-driving cars and UAV, unmanned aerial vehicles, and for medical applications, you may see that vision techniques are used for computer-aided diagnosis and so on. As the applications of visions are abundant, we believe that it is beneficial for RoboCup CoSpace Rescue participants to be familiar with vision techniques through a competition platform. Thus, we introduce CoSpace Rescue Vision for RoboCup Asia-Pacific RCAP Rescue University Category Advanced Challenge. And for your information, the RCAP CoSpace Rescue Challenge University category consists of 2 challenges, namely Preliminary Challenge and Advanced Challenge. Well, the Advanced Challenge will be the place the Vision Simulator is adopted. The simulator is equipped with both vision and LiDAR, and we believe the simulator would be a comprehensive environment for landing vision-based search and rescue in general, and navigation and mapping in dynamic environments in particular. So what is Vision Simulator? In this Vision Simulator, participants are still need to conduct search and rescue mission as in existing CoSpace rescue platforms. The difference would be the sensors available for the participants. In this simulator, each robot will have access to their own camera and LiDAR sensors. Then based on what they see through the camera, whether a color object, an aerial tag, or a landmark, they are supposed to navigate the field and conduct a search and rescue mission. Apart from camera and LiDAR, the robots are still accessible to other existing sensors like color sensors to pick up color objects, namely red, black, and cyan. Now, moving on to the second part. The simulator will have 5 new features in the panel as shown in the picture. I will go through the features one by one. First would be the map. So in this map, you can see that there are 2 differences compared to the existing platform maps. There would be deposit areas and traps. For the deposit areas, they will not be marked by colors anymore, so that cars cannot identify a deposit area by the color. Instead, cars are supposed to identify its own deposit area by detecting an aerial tag ID attached to the area as shown and go and deposit inside the area. The boundary of every deposit area will now be defined by a very thin line for reference to participants and for audience, but robots cannot sense that easily. Then, to add on the aerial IDs of deposit areas, the IDs will be different for red and blue cars, so that the cars will be able to differentiate their own deposit areas. The next difference in the map are traps, and aerial IDs are also incorporated to the traps, and their IDs are also different from those of deposit areas. You can still move around the selected car by clicking the area in the map image shown in the panel, and the car can be moved around in that way. The second feature would be the point of view, POV of the selected car camera. If the user wants to see the POV of the car to the platform, he or she can click the second button, circle in red, and can get the point of view image of the selected car. In case the participant wants to get a single snap image from POV of the selected car, the third button in red can be clicked, and the bitmap image of the third POV image will normally be saved in the file location shown. Also, for the POV videos, the participants can get a bitmap video of the selected car by clicking the fourth button circle in red. And since it is a video, the first click will start taking the video, and the second click will stop taking the video, and then the video will be saved in a file location shown. In this way, you can get bitmap images and videos. And the last features is that there will no more be X and Y map coordinates points available to participants to make better use of the camera and vision techniques. Now, in third part, I will discuss the basic navigation program provided with the vision simulator. As a basic navigation program, it will have functions to detect an object, namely color object and apron tag, in a point of view image. If there is an object of interest detected, the program will determine the X and Y image coordinate points of the detected object in that image. And then based on that information, the turning angle needs to tend to that detected object will be calculated, and the car will be driven in a way to make a turn to the object or to go to the object. Of course, other basic functions such as sensing the color objects on the floor to collect the objects and avoiding the obstacles are also implemented in this program. Now I will elaborate a bit more on how the snap POV image at a time from the camera will be processed by this program. At any time, a car can access the image data from the simulator, and that data will be fed to the image detection algorithm of the basic program. Then the detection algorithm will check whether the object of interest defined is inside the snap image or not. If not, the job is done, and the algorithm will wait for the next image data input. If yes, if there is an object of interest in the snap POV image, the algorithm will get the X and Y image coordinate points data of that object of interest and pass that information to angle calculation algorithm. Then the angle calculation algorithm will come up with the angle which the car needs to tend to head to the detected object of interest. The angle information is then passed to the motor driving function so that the car would be turned. This is generally how the program processes the image data and drive the car based on that info. The corresponding code for the functions in the flowchart can be found in the location shown. Now to give you a practical example of how an object of interest is detected, let's say there is a red object in an image, then the working process of the robot would be that first the robot will recognize that there is a red object. This action can be done by find blocks function from color patch data.h5. And then the robot calculates the position information of that red object. Again, this is done by find one block function from color patch data.h5. Then the robot will calculate the angle needed to turn to get to the red object. So that angle value is stored in object f rotate, which can be found in game one function from wall2.h5. After that, the robot drives to the red object and it will do the pickup. So for the driving functions, they can be done by setSpeed obj function from wall2.h and turn to angle function from wall2.h. So now I will demonstrate how the car will navigate in the field. So when you install the CoSpace Robot Studio, you will normally store it in C, and if in C, and you will go inside the CoSpace Robot Studio. Inside CoSpace Robot Studio, you will go to RCAP 2022, and you go to user, you go to this file, which is Vision AI demo, and you can open the project. So for now, I will be using Microsoft Visual Studio to open it. Okay, since I already opened one, I will delete this one. So you will see that there are total five files in this project. There will be one source file, which is ai.cpp, and there are also other header files, IPRETECH.8, colorpatch.8, global.8, and all2.8. So the IPRETECH.8 would be the file where the codes are responsible for finding the IPRETECH web store, and the code for the color patch or finding the color object in the image will be stored in this color patch.h file. And this global.h folder is where the platform variables are stored. Normally, you won't need to patch this one. And the ai.cpp is a source file. Here, you can save file some variables of the platform defined in this program, in this file. And the wall2.h is where the codes for the wall2 of the program is stored. So for the vision program, you are supposed to program only in wall2. So here you will only see wall2.h folder. Okay, so actually when we want to play our project to the CoSpace platform, we need to have a dynamic link library file, which is in short DLL file. So for that, we need to check object bit configuration. So you can go to project, and here you can go to project properties. So here the project name is CSR_AI. That's why you will see CSR_AI properties. And if you go to general, and if you check the configuration type, you will see that it's dynamic link library.dll. So make sure that your configuration type is DLL5 and press OK. And after that, if you bid this solution, your output would be a DLL5. So I will rebid the solution. Yeah, and you can also see the location. So if I go and check debug, and this CSR_AI.dll. So to be easily accessible, I will copy paste this file to my desktop. Then I will open the CoSpace platform. You can choose land, university, and practice park, and choose this map. And you choose CoSpace and click virtual again. So this would be a map of the vision simulator. You can see that the IPRETECH for the deposit area and the IPRETECH for the IPRETECH ID. Before I show you how to load the program and how to play the program in your vision platform, let me show you how to get the color ranges for the color object. So there are two ways to get the color ranges of the image. One way you can do is that you can use this color center value. So you move around, and let's say if you want to get the black object value, so put your color sensor above the black object, and you can see that this will be the approximate values for what you can use for defining the color ranges for your vision program. And the other way would be that you can get by clicking the Alt+I So a control panel will pop up. So let me show you. So first you need to click to control panel and press Alt and then I. So here you will see that the image color tab. And in this way also you can get the RGB value, or HSL value of the pixel. So let's see here, this is the black object. And if you put your cursor on the black object, you will see the RGB and HSL value of that object. So in this way, you can define the color ranges for your program. And you also see that there is an X and Y. So this X and Y is the image coordinate point. So here in this image, this would be 0, 0 point, and it will increase diagonally to here. So this X and Y image coordinate point will give you the information of the object in a particular image. So to load our program, click the load button, and this one desktop and this folder. So the program name now, the team name now is basic test, and we can run the program by clicking this. Okay, to see the point of view of the blue car, we can expand this tab, map tab, and click the second button. You will see that is the point of view of the blue car. And also, I will show you some backend info, so that you can clearly see what the car is doing. So you see that now is the car is making an attempt because the car sees a black object. So he's like turning to the black object to head to the object. That's why you see it's making an attempt. So let's run the program again. Yeah, now it's coloring the black object. Coloring black object again. Now he's turning to red, and now coloring the red object. You see that when he is sensing the boundary, you also know that there is a boundary, and that's why he's not going over the boundary. Okay, so to make it faster, let me modify the car a bit to see the apron tag. And what you might see later is that if the car sends the apron tag, you will calculate the position of the apron tag, and based on that position, you will make a tanning. And then you will go straight to the deposit apron tag ID, which represents the deposit area for the blue car. And then if he is near enough to the apron tag ID, he will do the deposit. Okay, let me try again. Now he sees the apron tag ID. You see that, yeah, he just go and deposit. After that, he leave, and then now he will continue the collecting the treasure, collecting the color object. Then we can try depositing again. You see that it make a 10, and sometimes it might miss, so you can make improvement on that. And let's try again. So that is how the program will be working. So it can collect the red sign and black object. And if the car see the object also, it can make a necessary turning. And of course, when you see the trap, you can avoid the trap. When you see the boundary, you can avoid the boundary. And when you see the aperture ID of the deposit area, you will make a necessary turn to head to the deposit area. And when it's close to the area, it's close to the aperture ID, then you will make the depositing. And I'll also show you the debug information for the aperture detector and color patch detector. For that, you can go down and comment this if that and that. So in this way, you can see that what is the tag ID and also what's the color object ID. So I will show you that. But when this one is for you to understand what is happening when you're running the program, but during the competition, you should not print any print statements in background yet. So let me build a solution again. Okay, solution now it's a fidget and let me, so the program is updated. Let me paste it here. And I will load the program, test start. Here you see that it's a color ID and then the center X and the Y. And also if you see the paper tag, you see the tag ID are printed. Yeah, so you see the tag ID is 3. Yeah, so that is also how you can get the debugging information printed out in the background. So also you can also run this program. Yeah, so this is how you can run the program, your own program in the vision simulator, and how you can do the debugging by printing out in the background. So let me start this program. And then let me go back to the presentation. So today we have provided the basic navigation program to you, and you can choose to improve that basic navigation program and learn the basic technique based on that. And the other option for you would be that you can use the library tools such as OpenCV or the neural network, the AI to detect the object of interest and retrieve the object information from the image. So in fact, your creativity is the key to drive and control your car in this vision simulator. So let me conclude the session. So in this session, I introduced the CoSpace Rescue Vision Simulator to you. And after that, I also discuss with you what were the new features in the platform and how the basic navigation program works. And lastly, I also made demonstration on the basic navigation program, how to build a DLL file and how to debug and so on. So I hope that from this session, you learn more about the vision simulator. And thank you so much for your time.